Hi everyone, in the last video of this semester, the gate all around the MOSFET is simulated. We start generating its structure. The structure shown in this video is generated based on some research papers on the gate all around transistors. In contrast to our previous examples, in this example, the wafer normal direction is positive Z direction, and for simplicity, 1 nano spacing is used for all three directions. Of course, you may improve the mesh. This is the silicon regions projected onto the XY plane. It is a top view. These numbers are written in the nanometer scale. The channel length is 12 nanometer. The channel width can be a design parameter. In this case, 10 nanometer is used. Of course, when you have wider channel, then this part will be wider. Also, this source and drain part will become wider according to the wider channel. The inner space length is 5 nanometer. This is a cut plane normal to the y-axis. Here we have a source and drain, and here we have contact and contact. This is the top nanosheet. Also, it is the middle one. It is the bottom nanosheet. Each nanosheet is 5 nanometer thick. For simplicity, we just use the 1 nanometer thick silicon dioxide layer. Of course, in reality, we must consider the high-K material. Between nanosheets, we assume 10 nanometer spacing. This is the full structure. It only shows the silicon regions and contacts. The contacts are highlighted. The gate is shared by 3 nanosheets. The inner spacers can be found here, although we have not shown them in this figure. Again, for simplicity, abrupt source drain doping profiles are adopted, and the intrinsic channel is used. These figures show the electrostatic potential at equilibrium. The metal work function of 4.5 electron volt is assumed. As studied in this course, the metal work function can be adjusted by changing the process conditions. This three-dimensional figure just shows the surface value. When we make a cut line, we can see the internal values. Top nanosheet, middle one, and the bottom nanosheet. Its IV characteristics are shown. The input characteristics at a drain voltage of 0.7 is shown in this slide. When the off current is below 1 nanoampere, the on current is about 61 microampere. At the on-current condition, the electron quasi-Fermi potential is drawn. Two-dimensional cut plane is introduced at the source end of the channel. This quantity is corresponding to the source potential. As shown in this figure, although the top nanosheet has a value close to 0.04 volt, the bottom one has a value close to 0.08 volt. Such a difference is originated by the voltage drop in the heavily doped source region. Since we have the on-current condition, the voltage drop is not negligible. Therefore, the bottom nanosheet is not as effective as the top one. Currently, we have 3 nanosheets in reality. Okay, that's it for this lecture 21. This is the last video for this semester. Thank you for your efforts.